So this video is going to cover the first part of our fundamental theorem of calculus notes. So, as it would suggest, as the name would suggest, the fundamental theorem of calculus is super important. This is going to be the backbone of everything we're going to do from now on. So the fundamental theorem of calculus, we talked about how Newton started with derivatives and Leibniz started with integrals. The fundamental theorem of calculus is what connects the two together. So we can see that there's actually a relationship between integration, finding the area under a curve, and differentiation, finding the rate of change of a curve. Okay, so before I actually write down the fundamental theorem of calculus, will come in two parts. Before we write down the first part, I'm just going to draw us a little picture here so we can be clear about what we're talking about. So I'm going to draw a little coordinate plane. And we're going to have a function, just any old function. And we're going to call this we're going to say y is f of t. So there's a reason we're going to be using a different variable. But it doesn't really matter what variable, I just don't want to use x. And that'll become clear. So, and we're going to say that we're going to evaluate or find the area under this curve from a to some unknown value x. So a to x, and x is changing. So x could be getting bigger and bigger, so our area could be getting more and more as we get more of the area under the curve. So we're going to say that g of x is the integral, it's a function, it's the integral from a to x of f of t dt. So that means g of x is a function where you plug in an x value and that becomes your upper bound. So that determines how much of the area underneath this curve you want to take. And the only reason for doing f of t dt is just so that it's a different variable than the x. So g of x means that x is that upper bound, that's our variable. F of t is just the function, and we write it in terms of a different variable so we don't get the two confused. Okay, so g of x is our function that finds us the area under the curve of f of t for different bounds, starting with a, but then our upper bound is changing depending on what we want it to be. Okay, so the fundamental theorem of calculus, part 1, says that if I have g of x equaling this function, the integral from a to x of f of t dt, so if g of x is the function that gets me that area under the curve for a changing upper bound, then if I take the derivative of that function, so I'm taking the derivative of that area function, essentially, you actually just get f of x. Okay, so this theorem is actually a really big deal. It's very simple, but very profound. It basically says if you have a function that gives you the area under the curve and you differentiate it, you take the derivative or find the rate of change, you actually just get the curve itself. So to actually prove this takes quite a lot of work. One of my whole college classes was dedicated to building up everything we needed in order to prove the fundamental theorem of calculus by the end. So we're not actually going to prove this, but I'm just going to show you a rough idea of why this is true. So we're going to use this visual we have here of that area. We're going to use this visual to talk about why this is true. So area, we're going to say that area is the same thing as our integral function, a to x of f of t dt. So area is that area function, or we could say that integral function. Okay, so we have some different areas. If you need a moment to take in this visual, you feel free to pause the video. So we have area of x plus h. So that means the area from here all the way up until this boundary x plus h. We also have area of just a to the x, area x. So that's from this lower boundary up until here. So you can see that x right here. So it's x versus x plus h. Okay. So what this is doing, we're going to look at the difference between the two. The difference between the two is right here. So on my screen, it looks like red. I'll do it in green. So the difference between these two areas is right here. So the difference between those two is about equal to that rectangle that you see drawn, which would be f of x times h, where h is that base. X plus h minus x. So the difference between these two areas is about equal to the area of that rectangle drawn in. So it's actually equal to that area of the rectangle plus some sort of excess that you see up there. So the difference in the areas is the same thing as that rectangle plus some excess. So what we're going to do here is we're actually going to divide everything by h. So we have the area of x plus h minus the area of x over h equals f of x plus the excess, it's kind of like our error, over h. So that left-hand side of the equation should be looking quite familiar to you. If I take the limit of this as h goes to 0, we'll have to do it to both sides, what does that left-hand side become? It actually becomes the derivative of a. You can look at the right-hand side, and what does that become? So f of x right now doesn't depend on h at all, so it's just f of x. So the excess over h part as the limit of h goes to 0, if you think about algebraically, you'd end up getting 0 over 0, which is indeterminate form, which we can't determine what that is algebraically, but visually, geometrically, we can see that as h goes to 0, that excess is going to be getting smaller and smaller and smaller. So that's actually going to go to 0. So then this is what we end up with. That area function, if you take the derivative, you just get the curve. So that's kind of a rough outline of the idea of what's going on here. So this connects integration with differentiation and is a really big deal. So we're going to use this fundamental theorem of calculus to find the derivative of functions involving integrals. So for letter A, we're going to have g prime of x. To find the derivative of this, all we do is plug x into our f function. So this is f of t right here. So all you have to do is plug in x, and that's it. It's really as simple as that. For b, h prime of x, we have, if h is the integral of sine of t over 1 plus t squared from 1 to x, all we do is do sine of x over 1 plus x squared. Letter C is a little bit different. What makes this one different is that instead of the upper bound being x, it's actually x to the 4th. So what's going on here is that we actually have a function inside a function. So this is our inside function. And then the outside function is the whole integral. So actually, when your upper bound is not just x, you have to use the chain rule. So we're going to do g prime of x is, we're going to plug that upper bound into secant of t. So it's just going to be secant of x to the 4th. But then we have to do chain rule on that inside. So it's going to be 4x cubed. And I'm just going to rewrite that as 4x cubed times secant x to the 4th. Okay, so if that upper bound, so all we're doing here is you're just plugging in the upper bound into your f function. If the upper bound is not just x, you have to use chain rule. So that's just the rule of thumb here. Okay. So what we're going to do now is we're going to look at this function. We're going to let f be a function whose graph consists of 2 straight line segments and 2 quarter circles. So we have 2 straight line segments. So we have this line segment, and then this is actually a straight line segment. And then we have 2 quarter circles. I'm going to go ahead and find the area of each of these parts because it's going to come in handy. So the area of this first section would be 1/2 base times height. So 1/2 base times height here would be 1/2 times 1 times 2. So this is just going to end up being 1. And then this is going to be 2. Okay, then our quarter circles. So a whole circle here would be pi r squared, which in this case our radius is 2, so it would be 4 pi. But it's a quarter of a circle, so this is just going to be pi. And this is also going to be pi. But remember that we, as convention, area underneath the x-axis is going to be negative. So what we're going to do is we're going to figure out what is g of 0. So g of 0 is we're plugging in 0 to our function. So it is the integral of f of t from 0 to 0. So we know from Tuesday that this is actually just 0. If the upper and lower bound are the same, that means that we're not actually finding any area. G of 4, however, is the integral from 0 to 4 of f of t dt. So that's going to end up being from 0 to 4 is going to be 1 plus 2 plus pi. So this is going to be 3 plus pi. 3 plus pi. So those 1 and 2 were just asking us to use the g function. 3 now asks us to find what is g prime of 1. So let's remember that g prime of x, in this case our upper bound here is just x. So we don't have to use any chain rule, it's just going to be f of x. So g prime of 1 is just going to be f of 1. And we're given the graph of f, so we just read f of 1 off the graph. This will be 2. G prime of 4 will be f of 4, which if you look at the graph is 0. And then g prime of 6 will be f of 6, which is -2.